Okay, we should be recording. So let me hand the floor over to the Pipette Group and have them share with us their design.
Are we ready to start?
Yeah.
All right, perfect. First, I'd like to thank everybody for coming out to our presentation. This is our presentation on our design for the Pipe Dreams automated pipette. The purpose of this project was to design a pipette that is capable of holding and dispensing up to 200 microliters. Our team consists of 6 UF students: Katie, Pablo, Alexa, Henry, Sergio, and myself, Tyson.
For a quick overview of our design, we created a pipetter that was able to perform basic pipetting operations with the capabilities of ejecting disposable pipette tips into a waste bin. Our pipetter features an easy-to-assemble design that integrates with a magnetic tool changer that's used in the bioreactor. The pipetter is able to perform fluid subtraction by pulling up the liquid by moving the plunger up, and from this point, the pipette can now expel all the liquid out by performing fluid addition. After pushing out all the liquid, the pipetter now disposes the used tips by pushing down further onto the ejector mechanism. And now we will go into more further detail about each subsystem for our design.
The overall pipette system was divided into 4 subsystems: the plunger and chamber, the ejection mechanism, the housing and collar, and a drive nut and a motor. The functionality of these 4 will be further explored in the following slides.
So the plunger and chamber subsystem is responsible for drawing in and ejecting liquid. It consists of a sliding plunger with 2 O-rings that fits tightly inside the cylindrical chamber. As the plunger moves up and down the chamber, it creates the necessary pressure difference to draw the liquid in or eject it. Both the plunger and the chamber are made out of stainless steel due to its corrosion resistance, cleanability, and strength. And we decided to go for off-the-shelf parts for these 2 parts because we wanted to reduce any possibility of surface imperfections that could affect the seal created by the O-rings. And for these 2 parts, the chamber is 6 millimeters in outside diameter and 3 millimeters in inner diameter and 48.7 millimeters in length. And the plunger is 2.5 millimeters in diameter, 69.5 millimeters in length. It has 2 machined grooves that will be used for the 2 O-rings, and it has a tapered end that allows for an easy insertion into the chamber. And from testing, this O-ring and plunger combination showed no signs of leakage.
So the O-ring and groove dimensions were designed with guidance from the Parker O-ring handbook. There isn't an exact principled method for selecting an O-ring and designing the groove because you usually need an O-ring to design the groove and you need a groove to choose an O-ring. So it takes some trial and error with both of them. Since we know the plunger and chamber sizes that were determined based on the volume requirements for the pipette, we used the handbook to help to determine the groove depth and gland width. We initially chose an O-ring that would be slightly larger than the inner diameter of the chamber, and this corresponded with a gland dash number 001. This allowed us to determine the gland width with no backup ring as 1 millimeter, which is also the same width as the O-ring cross section. Then moving on to designing the gland depth, our plunger outer diameter was closest to the range that corresponded with the smallest dash number, which gave a groove depth of 1.6 millimeters. This would mean that the gland depth would be 0.4 millimeters. And since the Parker O-ring handbook values were smaller than our actual values and moving up in a dash number would be too large, we chose to go with 0.5 millimeter gland depth and 2 different gland widths of 1 millimeter and 1.5 millimeters for testing. And the 1 millimeter gland width created a seal with no leakage that was verified later in testing. Additionally, we also used 2 O-rings instead of 1 to decrease the friction on the individual O-ring.
So for our ejection mechanism, we use a 3D printed part, a spring, and a hex nut to eject the disposable pipette tips. The 3D printed part was printed using PETG plastic at a 100% infill due to its strong strength. And the 3D printed part consisted of a sleeve that wraps around the pipette and a threaded end to attach a spring and hex nut. So for our ejection process, when the motor produces a downward linear motion onto the ejector sleeve will contact and push the tips off of the pipette. After ejecting the tip, the drive nut moves back up and the spring will retract the ejector part back into a neutral position to allow the pipetter to pick up a new disposable tip.
On the left is the overall outer housing assembly, comprised of two pieces held together by two 4mm rods to create a hinge and snap fit closure design. On the right is the inner housing collar where the motor mounts to the top face, with the drive nut and plunger constrained in the oval shape to allow for a strictly vertical movement and no rotation. Both parts are made out of 50% infill. The drive nut collar has cutouts on both sides that align with extrusions on the inside of the outer housing, so when the outer housing closes around the collar, it locks it in place to prevent slipping.
So to produce linear motion in our design, we used a stepper motor with a lead screw attached to the cylindrical 3D printed part that we called the drive nut. The drive nut was printed using PETG plastic at 50% infill. And as previously mentioned, the printed drive nut was fit into the collar to prevent rotation, which produced a linear motion when the motor was used. Plunger for our pipette is also press fitted through a hole near the center of the drive nut. The drive nut is a critical part of our pipetter design as it plays a major role in the functionality of our pipette, and the drive nut interacts with the ejector part to dispose tips and also interacts with the limit switch to ensure our design safely remains in the range so that plunger does not go past a certain distance.
Now, like all design projects, ours went through many stages of evolution. If one component was modified, the other components had to be modified to compensate for those following changes. Some of the major design changes include deciding to manufacture the chamber and plunger in stainless steel instead of 3D printing like we did for the rest of the design. As mentioned earlier, the purpose of this was to add a smooth finish, mitigating the possibility of air pockets occurring inside the chamber and avoiding leakage. Another notable design change is added snap fits to the outer housing in place of placing the pipette system in a simple box with the plate screwed on top, as you can see in the middle image. The purpose of this change was to simplify assembly and disassembly, further satisfying the customer need for toolless assembly. It also decreases the number of parts, decreasing assembly time and cost.
A tensile test was performed on a dog bone specimen of the PETG material that's used in the housing collar, drive nut, and ejector tip. The specimen was made with 50% infill since that's what was used in the housing. When we performed the tensile test, we determined that the tensile strength was 17.5 megapascals and the ultimate tensile strength was 27.6 megapascals. The tensile test that we performed on the printed specimen is not directly translatable to the print of our actual housing due to the orientation of the threads in the printing. Even though the infill was the same, the threads on the test specimen were created perpendicular to the threads on the housing. But we chose to perform a tensile test on the material in the housing because during one of our design iterations, the housing collar experienced a tensile failure, which will be explored in the next few slides.
With our design, under normal operation, the plunger does not need to completely exit the chamber. However, it is possible for the drive nut to be moved up higher such that the plunger comes out. In the case that there's a misalignment between the plunger and the chamber hole during reinsertion, an interference between components could lead to failure. Failure analyses were performed on the various components that make up the assembly affected by this overall mode. This includes a buckling analysis on the plunger, bending of the drive nut, heat insert failure, and tensile failure of the collar. From the section on power screws in Shigley's Mechanical Engineering Design book that relates the torque of a power screw to the force on the drive nut, we found that with our particular motor lead screw geometry, if the motor is moving at maximum torque of 0.5 Newton meters, then the force pushing the drive nut down is approximately 251 Newtons. Moving forward, any failure analyses based on this misalignment situation are performed under the assumption that the motor is operating at maximum torque. It should be noted that in a preliminary design, this plunger misalignment did occur and it led to a break in the collar where internal stresses overcame the maximum strength of that component. And a picture of that is shown on the right.
So The equation for buckling of a column was used to determine if the plunger would buckle under this failure mode. And it's noted that the plunger is fixed on both ends in this failure situation. So the equation for buckling of a column with 2 fixed ends is used, and the length of the plunger was taken from the face of the drive nut to the end of the plunger. Since the motor pushes the drive nut down with a maximum force of 251 newtons, this is more than the force to buckle the 3/16 stainless steel. It's worth noting that this is an unlikely failure mode because the housing would likely break before the steel plunger would break due to its lower tensile strength.
Now onto the drive nut bending stress failure. If we assume that the drive nut is perfectly rectangular and only the points of contact with the plunger and the lead screw are relevant, then the free body diagram looks like the cantilever beam figured on the top right. Furthermore, shear force and bending moment diagram were used to determine the bending moment and stresses. And the minimum drive nut thickness was determined to be 4.5 millimeters. Anything less would likely lead to failure from bending stress. As a result of this analysis, the thickness was increased to 11 millimeters, leading to a factor of safety of about 2.4. As stated before, during a preliminary test of our design, one pillar of the collar broke when the plunger collided with the floor of the collar. The free body diagram shown of the collar shows that fracture could have occurred because of tensile internal stresses overcoming the material strength. It is also worth noting that the material strength for the 3D printed parts largely depends on the orientation of the plastic layers making up the component. While the yield strength of PET-G layers under horizontal stress is 17.5 MPa as determined by our tensile test on the Instron, the same layers under vertical stresses have an 80% weaker yield of about 3.5 MPa. Furthermore, it was noted that during the preliminary test when failure occurred, the motor was improperly fastened to the collar with only half of the necessary support screws. This would cause an increased moment and internal stresses in one of the pillars and likely cause failure. After this failure, proper assembly was ensured. The cross-sectional area of the pillars were made thicker, and analyses showed that failure due to these tensile stresses would not be likely.
You muted, Henry.
Sorry. So for our ejection mechanism, we did a failure analysis on the ejected threads to ensure that threads do not break off during the ejection process. By using the maximum force produced by the downward motion of the drive nut and the force from the spring, we were able to find the forces that were acting on the hex nut. From there, we were able to calculate the bending stresses and axial stresses located at the 3D printed threads. Combining these stresses, we found the von Mises stress that was located at the threads, and we found that the maximum stress that the threads experienced was 22.20 megapascals. Using the yield strength of the PET-G at 100% infill, as given by our manufacturer, we found that the overall factor of safety for the 3D printed part was 1.35. Again, this is assuming that the motor produces its maximum force and that actual operations will produce a much lower stress.
So one of the main objectives from our design was to make sure that we could have a highly accurate pipette. The volume analysis started before we even manufactured a single part. In order to size the plunger and chamber, initial volume calculations were made using the size of the inner chamber and the volume geometry. Initial sizing resulted in an undersized system with a maximum volume of 150 microliters. And we think this is the result of an undersized tolerance in the chamber. We then redesigned the plunger and chamber for a maximum volume of 250 microliters, adding a 50 microliter buffer. Once we had our final plunger and chamber system, we obtained a calibration curve that you can see on the right. We obtained that experimentally, and it relays a number of steps that the step-up motor needs to perform to obtain a specific volume. And this calibration curve was coded into our Arduino code. So in the next few slides, we will show the testing equipment we used to calibrate our pipette. In these pictures, you can see the computer and wiring we used to control the motor and a scale we used to measure the weight of the fluid. From this weight, we determine the volume of the liquid that was injected from a given test. Here you can see the pipette in testing mounted to the test stand. And this is the final test that we performed to our pipette after it had been calibrated. We were asked to achieve a volume of 184 microliters. And from the test, we generated a volume of 179.98 microliters. Unfortunately, we were not able to be within 1 microliter, but we were able to be within 5 microliters every time. And that's just to prove that the weight, well,
As you can see here, the outer housing has 2 extrusions that align perfectly with 2 cutouts in the inner housing collar. Therefore, when the housing is fully shut with the snap fit, it'll lock the collar into place. There are also the same locking mechanisms on the other side of the assembly at the top of the collar. Here's the total assembly time based on Boothroyd and Dewhurst assembly timetables, which was estimated to be 5.5 minutes, which accounts for the first prototype taking longer to produce a new product. After a few iterations, it should be cut down to the customer needs of less than 5 minutes after multiple iterations from familiarity of the product and improvement of assembly time technique. Here's a pie chart demonstrating each subsystem cost for the first prototype of the pipette. In addition, there is another portion for the given components provided in the mech design lab. Some of the parts include the tool plate, magnets, PCB board, and battery contact pins. As predicted, the most expensive subsystem is the drive nut and motor subsystem due to the cost of the motor being $25.99. Here's a table clearly identifying the cost to produce the automated pipette. Part manufacturing is how much it costs to manufacture the chamber and plunger, which was calculated based on each process to produce the final part, such as the material and tool multiplier, geometry multiplier, unit cost, quantity, and overall process. Then the part cost can be separated based on the given components in manufacturing lab that were required parts in the design. The part cost for the non-given components comprised of every part and material we ordered and used in the final design and totaled by unit cost. Some of the most expensive materials used in the design was the PETG plastic filament, stainless steel plunger rod, and the stainless steel tight tolerance tube for the chamber. This also includes the $25.99 motor. Lastly, the assembly cost was calculated based on Boothroyd Dewhurst handling and insertion timetables from the previous slide. The total cost of the final pipette was $92.62. This cost estimate is from the total of the manufactured parts, part and material cost purchased, and assembly cost. Questions?
So yeah, this is Rick Miles with Northrop Grumman. I've got a couple of comments and then a question. So first off, I really appreciated some of the engineering calculations. Again, it's really nice to see hand analysis on this stuff. But one of the comments that was made when discussing it was, and again, this is just for learning purposes, someone stated that we feel that it most likely will not fail. So if you need to feel confident that it will not fail, you know, if you need to put a knockdown factor in to say that this covers our uncertainty or something like that, but just be careful about making those sort of statements, right? And then you were talking about the pipette volume and that you were not able to get within plus or minus 1 milliliter. I'd like some discussion there as to why you think you had issues with achieving that goal.
Yeah, so honestly, we think that that could have happened due to a couple of reasons. The seal was not a problem because we thought at the beginning that would be the most difficult part to achieve, that seal with the O-rings, but it would hold the liquid every time. But we don't know if it's an actual issue with the scale or that testing equipment we were using, because sometimes it would be within 1 microliter, but then after we repeated the test 10 times for a single volume, it would fluctuate a little. So that's why we decided to just report the 5 microliter accuracy, because that was what we actually could repeat every time. But honestly, it could be either the testing equipment that we used or that manufactured rod that we purchased. The inner chamber could have some surface uncertainty there that could affect somehow that volume. The volume was not completely linear. That's why we decided to calibrate it using that curve. So we would have like a more experimental approach to it instead of just theoretical calculations. But yeah.
Another theory of ours was also the motor we used, because we actually used the same motor as the other group that used the same volume pipette. And both of our groups had an error of 5 microliters plus and minus. And so because the only thing that was mainly similar in our designs was the motors used was the 1-start stepper motor, that was one of our main conclusions of probably why there was an error that was not really fixable.
Okay, thanks for that. Now, one thing, when you say that the uncertainty might be due to the testing equipment used, all the testing equipment should have some sort of tolerancing that then you can calculate an uncertainty to. So you can do an analysis there to see what the effect of the actual equipment is on that error and present that.
Yeah, that's definitely something we could consider. And also, if this was a project that would spend longer in time, we could try other motors and other ways to test it, definitely.
Thank you.
Thank you.
Hi, I had a question. I liked your animations, by the way. Those were nice to see some visuals, and I liked your calculations, but you were going into like that failure mode, but did you look at preventing the misalignment altogether? And did you look at the tolerance stack up of the assembly?
So under like normal operation, the plunger doesn't need to be completely out of the chamber, but since under a preliminary design, like that was the one time that like something broke, we decided, okay, this is probably an important thing to go over. And when we looked at it, I was thinking, okay, what would be affected by this? And there were several components in that overall assembly. So what we did was ensure that none of those sub components would fail, and that overall the motor would stall before anything broke.
Okay, thanks. For your O-rings, I was wondering, did you look at how much pressure they have to withstand, and did you take that into account in your calculations, in your design?
So I didn't do the pressure that they would withstand, but I did calculate how much they would be squeezed in the space between the plunger and the chamber, and that's detailed in our design report. And then also included in our design report is the static friction to, it's the force to overcome the static friction of the O-rings when they're lubricated. And it ended up being way, way lower than the average force that the motor is applying. So everything was within the specifications that we needed.
Okay, thanks.
Thank you.
So this is Rick Miles, Northrop Grumman again. I'll go with one other question. So down the road, this will be mass produced. You talked about 3D printing, right? Could you talk a little bit about if you had to go mass produce this versus making these one-offs with the 3D printing, how you would approach your analysis a little differently?
That's a really good question. So I feel like most of our design is pretty easy geometry wise, except of course that inner housing and we could say the outer housing, it's a little bit more complicated, but we try to simplify our design as much as we could. You don't really need any tools to assemble anything except just to attach the motor onto the top plate and the limit switches on the side. But if this had to be mass produced, then we would have to really think about probably making some changes to that inner housing and outer housing just to make it easier to manufacture. Maybe moving on to some different materials, or this was of course 3D printed. If we had to manufacture it using other methods, plastic injection molding or something like that, then the geometry would have to change a little just to adapt to that manufacturing process.
Okay, thank you.
Okay, we've got maybe time for one more question. 11:15 is the designated stop time. Oh, and now it's 11:15. Time's up. Okay. Well, I
Good
guess.
job, guys.
Thank you all for
Thank
coming.
you.
Thank you very
Thank you.
much.
Thank you so much for coming.
Thank you.
I also appreciate the comments outside of questions to allow us to pretty much to educate us, because we probably have more presentations down the line for other classes and future jobs, and it's very helpful. I really appreciate that.
Okay, well, let me.
It's fun.
Let me stop recording. There we go.